so again, single mode, very small core, 8 to 9 microns. Multimode has a larger core, 62 to 62.5 or 50. That's the answer right there. Single mode only accepts one mode of light. Multimode can have as many as 700 or 1100 different paths that the light can take through the core of the fiber based on the angles within the cone of acceptance, or the, right? So even though I can get more light, theoretically, into a multimode fiber, the different number of paths that it can take through the fiber causes me a problem, which we'll see. Single mode has to use very, very expensive lasers because they have to be extremely precisely focused. To get light into a 9 micron core, that thing's got to have a pretty good focus to it. Okay. Multimode, I can use less expensive lasers, VCSELs, or even LEDs, because the core is large enough to where it doesn't have to be such a precise light source, so it can be less expensive. The glass for single mode is less expensive to make than it is for multimode, particularly the newer varieties of multimode that are designed to support higher data rates. And we'll understand that a little bit more. But just understand that the process used for making single mode is much less complex than it is for making multimode, so the glass is less. We traditionally have used single mode for longer distances and multimode for shorter distances, and that's basically a cost-benefit type of thing. Multimode can't carry the signal beyond a certain distance, and so I have to use single mode for certain things. In an instance where I'm able to go shorter distances, I don't necessarily have to pay the cost premium for single mode. So that's been kind of the rationale. Single mode has the most bandwidth of all fibers, and in fact the most bandwidth of all media types known today. Multimode doesn't have that much, and we'll understand why in just a minute. The typical wavelengths that we use on single mode are 1310 nanometers in length and 1550, and on multimode it's 850 and 1300. Now there's some other ones that are used in wavelength division multiplexing, but we're not going to go into that because that's a little more complex than I think we're going to get today. Here's the answer. Okay. Why does single mode have more bandwidth than multimode? And again, it has to do with the number of modes. So with a multimode fiber, the older kind, there's the 62.5 micron, which they call OM1, a very old fiber. The slightly newer fiber that is 50 micron that they call OM2. The way the stuff is made is that I've got the glass that makes up the core and the glass that makes up the cladding, and they have different densities, and it keeps the light within the core. But here's what happens. When I shoot that light pulse into one end of the fiber, all these different modes start propagating. Well, the ones that travel straight down the center of the core get there first because their path is shorter, right? The ones that have to take the steepest angle and bounce around within the core of the fiber get there last because they've got the farthest path to travel. So look what happens to my on-off of the light, right? The light switch on and off real quick at this end. By the time it gets to the other end, the light pulse is spread out because all the different modes.
In time.
Right. So my receiver has a hard time saying, hey, was that a 1 or a 0? Which one was it, right? Okay, so how do we fix that? Well, with the higher grades of fiber, which are the 50 micron, OM3 and OM4, those are the terms used for them. And what's important about them is that they're called laser optimized fiber. Here's what they do. It's pretty cool stuff. They dope the core with chemicals that actually make the modes that have the shorter distance to travel slower, right? So the ones that have the ones that have the longest path to travel fastest. The ones that have the shortest path to travel, they've actually doped the glass to make it travel slower. So it takes that input pulse and it retains much more of the shape, which means I can send it farther and I can send more information because I can modulate it more fast, more quickly. Okay, make sense? And those are the two primary differences between the multimode fibers. Step index, which is just glass to glass, graded index, which is doped to slow down the modes in the middle. Single mode, do I have to worry about what this is called modal dispersion, by the way? Do I have to worry about modal dispersion with single mode? Why? Because there's only one mode. Only one mode, one path. Right. So single mode retains that waveform a whole lot better for a whole lot longer distance than either of the multimodes. Make sense? Okay. All right, but there are losses that are associated with all kinds of fiber. Obviously, modal dispersion is the big problem for multimode, right? And the more things we can do to fix that, the less problem I'm going to have with this pull spreading. Okay. Well, single mode isn't actually, it's not subject to modal dispersion because there's only one mode. It suffers from what's called chromatic dispersion. What that means is that my light source here, right, it may say it's a 1550 nanometer laser, but it's not just 1550 nanometers. It's a range, somewhere between, say, 1530 and 1570. Okay. That range actually incorporates, if you think of it this way, different colors of light. There is no color because it's beyond our ability to see it, but if you think of it the same way, 1530 has a color, 1550 has a color, 1570 has a color, they're all different, they all travel at different rates. Okay. So single mode is, the big problem for single mode is chromatic dispersion. All right. It's not a huge problem because it doesn't usually start to become a problem until way down the line, but that is the major function of loss for single mode, is chromatic dispersion. Both types are subject to what's called Rayleigh scattering. Optical fiber glass is extremely, extremely, extremely pure. And again, they add dopants to it to make it do special things. But even as pure as it is, it's still going to have impurities in it. Okay. And what happens is when the light strikes those impurities, it causes reflections that will throw the light outside the critical angle and out of the core of the fiber. So you'll have loss that's associated with impurities in the glass. Okay. These again aren't huge issues as much as like modal dispersion is, but it's something that has to be accounted for. And when you look at fiber cable, it will say this is the modal bandwidth per kilometer.